Hello students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today we will continue our discussion on Lotka Volterra model for competition. So if you remember in our model, we had two species, rabbit and sheep, and they were competing for the limited resource of grass. And our model looked something like this. So if you look at the model, we have rabbits and sheep, and their growth, their net growth is governed by logistic model. So rabbit and sheep, in absence of competition, will undergo logistic growth. And then because the resource is limited and they are competing for the same resource, they have a competition term here. One thing that I wanted to explain to you was that the negative sign before the competition term shows that because of competition, both the rabbit and sheep are at loss. They are not benefiting from it. However, the rabbit faces twice as much loss as sheep does in this rate equation when it comes to rate at which rabbit population is changing. Now, in this scenario, where the competition between rabbit and sheep affects more rabbits than it does sheep, this is the phase portrait that we arrived in. Now, here on x-axis we have R, which is rabbit. On y-axis we have S, which is sheep. Now, one thing you need to note is that this model is not to scale. Now, it is quite possible that 3 does not exactly mean 3. For example, here one of the fixed point is at 3, 0, which means 3 rabbits, no sheep. This does not mean we'll be left with only 3 rabbits and no sheep. What it means is that 3 units of rabbit and 0 units of sheep. Now, the unit may be 100, maybe 1000, 400. That right now is not known. This is an example. So please do not assume that in competition the fixed points are 0, 2, 1, 1, 3, 0 and 0, 0. And any more or less of the rabbit and sheep are not really at fixed point. That is not what is happening here. Now, since it is competition, I think it is helpful for us to dwell a bit on the phase portrait and look at what it is trying to tell us. So if you look at the phase portrait and just the first quadrant, because we are dealing with real natural numbers, rabbit and sheep, they are natural numbers, we can't have negative values of them. So I'm going to ignore the second, third and the fourth quadrant. So if you look only at the first quadrant, if I start with 0, 0, which is an unstable fixed point, if my ecosystem that has only rabbit and sheep, we somehow end up eliminating both rabbit and sheep, then the rabbit and sheep will not come back because there are none left. However, even if there is some rabbit to begin with, so basically R is in the neighborhood of 0 but not at 0, and same thing is true with sheep. The 0, 0 being an unstable fixed point, it means it will push the rabbit population and sheep population away from 0, 0. Both rabbit and sheep will multiply until contained by either their competition or by logistic growth model, which is resource limitation. One thing I want to clarify here, in the model we have two minus signs. So we have plus signs for the growth and then we have two minus sign, one is the resource limitation and one is for predation. It's very important to be clear that in resource limitation the rabbits are competing between the rabbits, they're competing with each other. So here resource limitation. I'm going to highlight resource limitation. The rabbits are competing with each other. So when two rabbits compete with each other for the same resource, another way to write that term would be to multiply the population of rabbit with the multiplication of rabbit population. Like in case of competition, when rabbit and sheep were competing for the same resource, what we did was we multiplied rabbit population with the sheep and then added a coefficient in front of it. Similarly, in case of resource limitation, since the competition is between the same species, we multiply the population of the species with itself and end up with the square term. That's another way of looking at logistic growth. It's basically competition between the species for limited resource. So to summarize, logistic part of this model is competition between the species. And the competition part is competition between different species. So, between the same species is logistic part. Okay, so what happens when rabbit and sheep are competing both with members of their own species and members of another species, which for rabbit is sheep, for sheep it's rabbit? This is a face portrait we get. And in the last lecture, we learned how to arrive at the face portrait, but I want to spend some time looking at the face portrait and understanding how to interpret it, because just coming up with the face model is not sufficient. The model should be able to help you predict what may happen in future or what may happen if we change the circumstances and how things behave. This face portrait shows a very interesting scenario. There are 4 fixed points: 0, 0, 0, 2, 3, 0 and 1, 1. We discussed this earlier. One face point, which is 0, 0, is a face point of total annihilation. Which is both rabbit and sheep are dead. There are none of them. The other 2 fixed points that relate to annihilation of one of the species are 0, 2 and 3, 0. This is extinction of one species. And I have shared this before, we are right now undergoing the 6th mass extinction event in our Earth, on our planet, in the biosphere. And here we are taking example of 2 species who are competing with each other. And there are 2 fixed points that talk about extinction of one of the species. In a complex environment, in a complex ecology where we have hundreds of thousands of species in a given ecosystem, these models will get incredibly complicated very fast, because all the species depend upon each other, both flora and fauna. Okay, so 0, 2 and 3, 0 refer to situations, fixed points that correspond to extinction of one species. 0, 2, extinction of rabbits; 3, 0, extinction of sheep. Now notice one thing, when rabbits go extinct, which is 0, 2, this one, let me highlight it, this fixed point, we have 2 units of sheep. When sheep go extinct and we have rabbits, we have 3 units of rabbit. Right here we can understand that the carrying capacity of the ecosystem is more for the rabbits than for sheep. So, in nonlinear systems, please don't look at this part. Oh, this part is the logistic part. So basically the carrying capacity for rabbit is 1 unit, the carrying capacity for sheep is also 1 unit. Don't do that. You have to look at the competition term also. And the best way is to actually find the fixed points and then try to understand the behavior of the fixed points. Okay, coming back to our face portrait. So then there is a 4th fixed point, which is 1, 1. And this is a fixed point of coexistence. Before the current 6 mass extinction that was triggered by our human interference, there was a gradual evolution of species, gradual extinction of species. But mass extinction event is definitely done by humans. Now, what we have done is we have destroyed the balance, the delicate balance between the numbers of species. And we can look here. 1, 1 is a saddle point. Now, what does that mean? 1, 1 being a saddle point, it means we'll only arrive at 1, 1 at the fixed point of coexistence if we are on this line. Let me highlight the line for you. If we are on this line. Now, this is one line in an entire face portrait. So, there are incredibly limited number of initial points compared to all other possibilities where rabbit and sheep can coexist in this ecosystem. Any other scenario, if any initial point that does not lie on this line, and please note that I've highlighted the line, so the line looks much thicker than it is, just a string of points which are infinitesimally small. Any other starting point means that either of the species is going to extinction. So let's look at which domain of initial points will result in extinction of sheep. I'll use another highlighting color for it. So if our initial starting point is somewhere here, so this is a light salmon color. I don't know what color it's showing up on your screen. But this zone of the phase portrait, if our initial point is anywhere here and you continue this to infinity, then at the end what we'll end up with is extinction of sheep and only existence of rabbit. Even if we just compare the number of fixed points and or the probability of us starting on the line where we'll end up with coexistence, which is the green highlighted line, versus the area where if our initial condition lies there, we'll end up with extinction of species, it's pretty clear that coexistence is a very delicate balance. It's very improbable. Now let's look at extinction of rabbit. If we are in this zone, if our initial condition is in this zone that I've highlighted with the light blue, then we are going to end up with extinction of rabbit. Another thing it tells you, if we start at the line of coexistence, it is the perfect line for both species to coexist. But if we end up having more rabbits than sheep, let's say we are starting at this place, let's say we are starting at this place in the line on the line, and this is a point that lies, initial point is here, and it's a point that lies on the line of coexistence on the unstable manifold, which is where the direction is towards 1 fixed point, which is the fixed point of coexistence. Then eventually rabbit and sheep will coexist, 1 unit of rabbit, 1 unit of sheep. However, if we end up adding more rabbits or if we reduce the number of sheep, we'll end up in this light salmon color zone. So if we have more rabbits than we need to be on the line, we'll be somewhere here. And then eventually we'll end up with elimination of sheep. If instead of starting here at our initial point on the line, we are starting, let's say we are reducing the number of sheep, but we're keeping the number of rabbits the same. So we'll drop down here. And again, we'll end up at our extinction of sheep fixed point. On the other hand, if we start with more sheep, so we have more sheep than rabbits, the required to be on the line, then we'll be somewhere here and we'll end up with extinction of rabbits, only sheep present. Or if we kill some rabbits when we are here, then we'll end up somewhere here. And then once again, we'll end up with extinction of rabbit. The whole point of showing this to you was to notice how delicate and in a way improbable coexistence is. It does not just justify the current mass extinction at all, but it tells us how just delicate the coexistence in ecosystems are and how important it is to not disturb the natural ecosystems that we know are balanced, how important it is to preserve them. Because if we reduce or increase the number of one species, it will take the initial point away from this line, the line where we have unstable manifold. Okay, so this was Lotka Volterra model for competition for you. Now I'm going to teach you how to use exactly the same principle and write model for predation. Now this system that I'm going to teach you, I want you to pay special attention to it, because in one of the upcoming lectures, we are going to use exactly the same approach and we are going to model limit of growth, which is very important for all of us to understand right now. Limit of growth are not new models, but the whole concept of limit of growth was that GDP can't continue to grow forever, and we'll discuss in one of the upcoming lectures. But even when we are modeling the effect of GDP growth on climate and how much can we allow capitalism to grow, we can use very simple principles that we use in Lotka Volterra model. Now I must tell you that Lotka Volterra models are not without limitations. There are limitations, and once I'm done with Lotka Volterra model for predator-prey and for cooperation, I'm going to teach you the limitations of Lotka Volterra before we use it to apply on greenhouse gas emissions and GDP growth, which is limit of growth model. Okay, so here we have our model, Lotka Volterra model for competition, and we are going to use the basic methodology of writing this model to model predator-prey relationship. So we have two species, one is a predator species, the other is prey species, and they are coexisting in an ecosystem. Alrighty, so let's say we have two species. For this model, let's say sheep and fox. So we have fox df by dt and we have sheep ds by dt. Okay, so let's say the sheep will undergo logistic growth and they will look very similar to the growth that we saw here. So we have 2s minus s square for the sheep. But sheep are not the only species in the ecosystem. We also have fox that are eating it. Every time sheep and fox interact, the sheep is killed and becomes food for the fox. So we clearly have a system here where it's something like SF. The interaction, very important to understand. Why are we multiplying the number of S and F? The interaction between sheep and fox, the probability of that interaction would be this, would be related to the product of their populations. That's why. And let's say we are using 1 unit here, but again, I do not know what the exact coefficient will be in an ecosystem like this. For an example, I'm using -1 here. Okay, now let's look at fox. Every time fox hunts a sheep, because the fox can't eat grass. Now, since fox and sheep are not competing for grass, sheep is running out of grass because grass is limited, and that puts a resource limitation on the sheep population. So what we have in this particular model that I have written so far, we have again 2 subtracting terms. So there are 2 things that are reducing the rate of growth of sheep. This is competition of sheep with members of their own species because of resource limitation. So this is again very similar to what we were seeing here, competition between the same species for resources. So this is the resource limitation part. What we are seeing here is predation. So even though this model for sheep looks very similar to the model of competition for between sheep and rabbit, the SR here and the SF here are very different, because SF is the term for predation, not for competition. Now let's look at fox. Every time the fox hunts down a sheep and eats it, it benefits. It gets calories, it gets the energy and the nutrients it requires to grow in number. So SF, every time this predation happens, it is reason for fox to multiply. So the growth pattern of fox will look like this, SF. Now the fox are not competing for grass, so we do not need a grass term. One thing we need to understand is that fox are competing amongst each other for sheep. So the fox, they want to eat the sheep, and if they start running out of the sheep, then some foxes will start go hungry. So at some level, there is a competition happening between the foxes for sheep. So we have minus F square. Now please note here, foxes are competing with each other. This is not resource limitation. I need to write this down. This is very important, and I would love to ask you questions about this in the exam. S square here refers to resource limitation. Resource here being grass, sheep are competing with each other. F square here is talking about, again, a competition between the foxes. We'll call it interspecies competition. No, intraspecies competition. Intraspecies competition. Okay, it's not same as resource limitation in environment, which is typically what logistic resource limitation is about. It is resource limitation in the environment. Here, it is another animal that they are competing for. So this is more similar to these terms here, the third terms here in the competition model. Apart from this, there is no other reason for fox to die. There is no other reason for fox to suffer. Every time it hunts a sheep, it grows. Every time it does not, it's not able to hunt. It's not growing, it's not replicating, it's competing with each other. Okay, now we are going to solve this. So let's write the Jacobian matrix for this. So to summarize, our model looks like this. Yep, that's correct. Okay, so we are going to write Jacobian. Now remember, Jacobian, we'll have to do partial derivatives. So let's say this is the first model F, and this is G. So our Jacobian will look like this. So we are going to differentiate this equation partially with respect to f, and then again this with respect to s, and we'll repeat similarly with the second equation g. Oh, there's a small mistake here. It should be del f. Okay, so this is what our Jacobian looks like. Now we need to find the fixed points. We need to understand how many fixed points are there and what they are. So we can factorize this and write simply as okay, so this is for fixed points, both df by dt and ds by dt should be equal to 0. So we are going to solve this and we are going to see how many fixed points we come up with. So one obvious solution here is that both f and s are 0. So if both f and s are 0, the first fixed point we get is 0, 0. Right away I can tell you this is going to be an unstable fixed point because we are dealing with a growth model. So 0, 0 needs to be an unstable fixed point, otherwise there's something terribly wrong with our model. So f is not equal to 0, which means s minus f has to be equal to 0. So we get s is equal to f. We can put this here and we end up with either s is equal to 0 or s is equal to 1. These are the two situations we end up with. Since s is equal to f and f is not 0, s equal to 0 cannot be the answer. So if when f is not 0, then s and f both are 1. Okay. Let's look at another scenario when s is not equal to 0. If s is not equal to 0, then what we have is s plus f need to be equal to 2. Okay, now we can take this information and we can place it here. So basically what we have here is that s is equal to 2 minus f. We can place this here. And we end up with f is equal to 1. So when f is equal to 1, s is equal to 2 minus f, so s is also equal to 1. So we arrive at a very similar fixed point, 1, 1. This is a very interesting scenario. I need to change numbers to make it a more fun example. Okay, now in both these cases we have arrived to the same answer. So either both s and f die out, both foxes and sheep die out. Let's say sheep get some disease and they die out, and then the foxes will die out. Or on the other hand, if both are existing, then both will coexist. And this is a very interesting example. So let's try to draw the face portrait. Let's try to see how the behavior of foxes and sheep happen around these two fixed points. So we have only two fixed points here. Okay, so the Jacobian at 0, 0 looks like this. So here the tau is 2, delta is 0. Okay students, so we have a very interesting scenario here where tau is positive and delta is negative. So if you remember your diagram, sorry, delta is not negative, delta is 0. So if you remember your diagram, tau is positive, delta is 0. Tau is positive, delta is 0. So we are here in this top part of the y-axis. So we are dealing with non-isolated fixed point. Okay. Now let's see what happens at 1, 1. So let's put the value 1, 1 here, and then what we get is minus 1, 1, minus 1, minus 1. So in this very interesting scenario, tau is going to be minus 2 and delta is going to be 2. Now let's look at tau square minus 4 delta. 0. We are on the curve. Tau is minus 2, delta is plus 2. So let's go here. Tau is minus 2, right? So we are at the bottom side of the graph, and delta is plus 2. We are at star or degenerate node, and it's a stable scenario. So basically, if what this system is telling me that when sheep and foxes undergo such relationship, then coexistence is actually going to be very likely for them. They are going to coexist. And this makes sense because let's say we start running out of sheep. So if let's say sheep is tending to 0, we are running out of sheep. What will happen is as the sheep start numbers start going down, SF will start going down rapidly. So the growth rate of foxes will be determined predominantly by minus f square. So instead of growing, the foxes will start dying out. And as the foxes will start dying out, this number will start going down, which means now the sheep has time to increase the number. So in this particular case, what we see is that coexistence is very likely in the predator-prey relationship when, now this is conditional, when the predator relies for their existence completely on the prey. And if you are running out of the prey, then the predator population goes down. And as the population of predator goes down, then the population of the prey can bounce back. So very interesting example. Now, however, something very fascinating can happen here. If I change the coefficients, let me clean up a little bit. If I change the coefficients here, for example, let's say I say 2SF, which is every time a sheep hunts a fox, every time a fox hunts a sheep, the successful hunt of the sheep will allow double the benefit for the fox. So more foxes can eat the sheep, live, and then produce young ones. So let's say instead of 1 SF, it is 2 SF here. That might change how our behavior is around the fixed point. That might change how our face portrait looks like. So don't assume that predator-prey relationships are perfectly and going to end up in coexistence. It's just happens to be the case in this particular example that I gave you. It does not have to be the case with other examples. In the next lecture, what I'm going to do is, I'm going to return back to the Lotka Volterra model of competition, and I'm going to show you that how by changing the constants, we can end up with very different results. That's all for today. Thank you.